computer.
Sweet.
Okay, you're good.
Sweet. Welcome to West Coast Machine Learning. This week we are going over a paper from Prime Intellect called Recurrence-Complete Frame-Based Action Models with the subtitle Long Horizon Perception Requires Rethinking Recurrence, which I thought was kind of an interesting iteration on a couple of ideas that are sort of related to the ones that we were working with last week, i.e., the two papers that came to mind were the harnessing the universal geometry of embeddings, and then there's another one called theoretical limits of embedding-based retrieval. And the reason that kind of relates to this paper is there's all sort of basically it's like a series of papers. They aren't necessarily a series, but if you were to think of them as that, they sort of go over some of the fundamental limitations of the transformer architecture. And historically, transformers have been very important. And all of the largest AI models, all of the frontier models are generally transformer architectures. We really have not found one that is just straight up better, largely because transformers scale really, really well, proportional to the amount of compute that you give them. One of the reasons that they scale very well is that they are inherently feed forward and fully parallelizable. So the reason that this is important is because GPUs, the kinds of computations that they are very good at is computations that can be done in an embarrassingly parallel fashion. So they're not necessarily more powerful machines than CPUs, but they are better at parallelization. And then we try to take advantage of that with transformer architectures that we can scale up by throwing additional compute at them. But this introduces a couple of limitations because of qualities like inherent feed forwardness and like because we're doing back propagation through time and because we're relying on gradient descent, there are some types of functions or ways to process information that are not well suited to architectures that are capable of this sort of embarrassingly parallel kind of configuration.
Hey,
and one of these, yeah, what's up?
Yeah, just one question. You
Mhm.
you said that they're inherently or we're using back propagation through time. The
Mhm.
transformers don't do back propagation through time, do they? They just do straight back. It's a feed forward, so it just does a back propagation.
Let's see. For transformer architectures, do they do BPTT or just vanilla backprop?
Yep.
Let's see. Yes, I technically don't really know the difference. Do you happen to know the difference off the top of your head of backprop versus back propagation through time? I don't
Yeah,
really know the term that
yeah,
well.
yeah. I mean, when you have like an R and N where it's recurrent, then you essentially kind of propagate through the same weights multiple times for each. I don't know what you call it, each stage. Um,
Hmm.
and those are the ones that are harder to train because it ends up being really deep, essentially.
Oh,
Yeah,
okay. Interesting.
yeah,
Yeah, I didn't know that BPTT was a distinct term necessarily from the other kinds of backprop that we do for
yeah,
transformers.
yeah.
Um, but yes, that is sort of the core premise of this paper is like transformers don't have a recurrent hidden state that's reused across time steps, so you don't unroll through time.
Right.
This is actually a the conjecture of this paper is that because you're not doing that, there are some kinds of information processing that no matter how much compute you throw at it, you're never going to be good at it.
Hmm.
Um, so that is traditional vanilla backprop, not BPTT. And all of our biggest models rely on that. So one of the sort of things that makes one of the limitations that causes is a formal restriction on their ability to learn or execute classes of temporal algorithms that require serial causality. The lack of native causal sequencing manifests as recurrence failures in long-term stateful reasoning, e.g., self-referencing inconsistencies and hallucination loops, et cetera, et cetera. Basically, the thing that this is getting at is when these transformers are producing tokens, the way that they are utilizing their attention mechanisms is in a parallel fashion, and because they're doing that, it's going to they're going to naturally be quite restricted when the thing that they're trying to do needs to happen in sequence, as opposed to like, well, it would be better if you did it in sequence, but you can do it in parallel, which is sort of the approach that all of our largest models end up having to take these days, where it's like, okay, I need to sort of pretend that I can do things like, recursive reasoning or sequential causality by doing a process in parallel that produces similar tokens to someone who would be doing this thing in series. So you can sort of kind of get around this, but end of the day, the architecture is just not capable of doing some of these things. And it turns out that there are a couple of tasks, a couple of new benchmarks that they propose in the paper that point out that this particular limitation is actually a pretty big one for a pretty large use case, which we'll get into in just a second. So the goal of the paper is, well, let's presume we're right, that we have some fundamental limitation because of our lack of parallel, or our insistence on parallelism here. And let's try to design another architecture that's going to be able to do those kinds of tasks that hopefully scales, that is recurrence complete. So next one, this got a little janked up, I think. But here we're going to define a couple of terms. One is recurrence completeness. I wonder if I like maximize this, will it? No, it won't. Okay, I tried. The architecture is recurrence complete if it can represent general recurrent updates for general non-associative stuff. Man, I should have fixed that. Let me see. Non-associated implied solutions cannot be computed without sequential inference. And then let's add this here too. And then we're going to tell our little assistant, elaborate. Elaborate. So we have our foundational theoretics here of recurrence completeness. Basically means that the network needs to be able to represent general recurrent updates. It needs to be able to do computations that require sequential operations. And we will, if it is capable of doing that, and I think there was like a point here that they made for general non-associative something. Recurrence complete if it can realize general recurrent updates for arbitrary transition functions, including non-associative ones. Non-associative here means you can't legally reorder or regroup the sequence of updates into an equivalent parallel scan. The exact serial order matters. They touch on that a little bit too when they're defining these terms. True depth is if your architecture is recurrent complete, i.e. it can implement those general computations, then for some inputs, there is no way around an, is that omega of n, chain of dependent steps. Worst case, true depth grows linearly with sequence length. Let's see. if it is that, then for some inputs, yeah, so some of these inputs, if your architecture is RC, then for some inputs, there is no way around a chain of dependent steps. So you have for some of the things that that network is trying to learn, there will be some of them where you don't need to like have this sort of like causality tracking mechanism here. But for some of them, you will be unable to process that function in the network without kind of going this route of like, okay, now we need to figure out causality and stop parallelizing. So worst case, true depth grows linearly with sequence length. And then we have there's a couple of proofs in the paper that model the computation as a DAG of unit cost ops. If each h of t plus 1 depends on h of t, then h0, h1, hn is an ancestor chain of length n. That forces true depth of less than n. If G happens to be associative or scannable on that particular task, you can get sublinear depth. But RC demands that you can also do the non-scannable cases, which pin you to the omega of n in the worst case. So long story short, the things we're defining are recurrence completeness, i.e. the model can do this sort of recurrent operation that we're talking about, and then true depth of like, for a given sequence, can you get it done with like an associative or scannable approach? If so, then that's great, but we don't care. The thing that we care about is true depth, i.e. for those operations, which are the kind or like which inputs are the ones that we're gonna need to do in series, and then what bottleneck does that put on us effectively? And then impossibility theorem is any architecture whose forward or backward pass is fully parallelizable cannot be recurrence complete. This includes constant layer transformers and parallelizable RNNs. So there's been several other kind of like not quite transformer architectures that have popped up, like RWKV, or Mamba, if anybody's familiar with the selective state space series. The argument here is that, hey, like it's not just transformers here, it's anything that you can fully parallelize on forward or backward is not going to be capable of those, is kind of the stronger claim here. I'll pause for a bit. Any questions, thoughts, comments, concerns so far?
Nope.
Take that as a no. Let's see. Two complementary ways rules time parallel architectures out of RC. So forward or backward parallelization is not, and then concrete families that fall short. Efficient are listed as not recurrence complete because their aggregation and backprop can be organized with sublinear true depth, i.e. they never realize the required serial chain. The input aggregation criticality is our problem here that we're defining. In input length proportional tasks, correctly aggregating observations up to time t requires some number of truly sequential steps. I think we get to it a little bit later on in the presentation, but this sort of relates to a concept that Wolfram talks about every now and again, Stephen Wolfram, called computational irreducibility, in which you are unable to predict the results of the computation. Sorry, one sec. You are unable to produce the results of the computation without actually performing the computations in sequence, because you need the states of all of the previous ones. Mechanism of failure is we have bounded true depth per layer stack. Aggregation criticality marks the maximal sequence length n, beyond which the model can no longer form the correct latent state. As n over L grows, representational fidelity collapses. I think there's an interesting interesting. Let me see if I can find it in the paper. Latent, I believe. Yeah. Related failure mode. Let's see. A task property that makes these limits operational. Input length proportionality. In such problems, correctly aggregating those requires that number of steps. No parallel reordering or associative scan eliminates that dependency. So we'll formalize a failure mode for time parallel models, which is input aggregation criticality, the maximal length beyond which a non-recurrence complete model can no longer form the correct latent state due to a bounded true depth per layer stack. So the way that I'm interpreting this is that there's going to be what you need to do is some amount of state tracking. And the way that you would do that if you're a model is to sort of iterate on that sort of hidden state object repeatedly during the length of the sequence as you're predicting. And what they're conjecturing here is that latent state that you need to, in order to be able to actually track this, unless you're recurrence complete, you are unable to represent that inside the model. So you will predictably always see this fidelity collapse. And the reason that you'll see it is because of this aggregation criticality limit. The real world examples, which are like fairly significant ones, being agentic state transitions, code-based diffs with side effects, complex inventory and ledger tracking, any regime with latent variables and state mutation. So this is like almost all long horizon tasks. So the implication here being that without, at the very least, access to some kind of like external module that gives it this, that can kind of overcome this limitation of recurrence completeness, the no matter how smart you make the model or how much compute you throw into that network, it's never going to be able to do enough internal state tracking to be able to be used in those contexts.
So Warren, am I understanding this correctly then? So true depth is kind of referring to, if I think in terms of transformers, true depth is going to be what's the maximum sequence length that the transformer can represent. Is that right? So it's an attribute of the model. Is that true? True.
So I don't think that is true depth. I think that's the aggregation criticality, if I'm not mistaken.
Okay.
The formal related failure mode for a time parallel model, i.e. a traditional transformer, is the quality of input aggregation criticality, which is the maximum length beyond which one of these models can no longer form that correct latent state.
But it said due to bounded
true depth.
True depth per layer stack.
Oh, I see what you're getting at. Yeah. So
They're equivalent.
Yeah. So we have the thing that we're doing is we are looking at in the layers that transformer has access to, how many of them have a true depth, and then there's going to be a point at which that true depth quality, once that's too long, the conjecture is like you're done. You're not going to be able to solve this problem, basically.
Okay. And then there seems like, in my head at least, there's an inversion of meaning. So recurrent complete means that it can't represent kind of infinite sequence. Is that right?
Recurrence completeness is the quality of being able to realize general recurrent updates for arbitrary transition functions, including non-associative ones. So the transformers are not recurrent complete because they cannot do that.
Okay.
Mm-hmm.
Okay.
Cool. Let's see. All right, next one. Hey, it's an animation. They tried. This is where we start getting into the architecture of like, okay, if we presume that all of these problems are actual problems, how do we solve them? And that is with another kind of neural network architecture called here, or referred to here as RC-FAM. The idea being we will have a high throughput transformer frame head with intra-frame pooling to embed the current frame. So the idea is, let me see if I can find like how we define a frame there. There we go. To study this regime at scale, we introduce a frame-based action modeling setting. Each time step provides a frame, which is a complete fixed-size 2D view of the interface, i.e. like a terminal. And then that's paired with the next low-level action, which is like a keystroke or a control sequence of some kind. And then we can compile that data from Git histories by reconstructing plausible editor sessions and then capturing the resulting terminal frame buffer with a some capture stuff. The results being text and video and actions, which are a good sort of basis to operate these models. So the idea is we're going to take those frames and then we're going to make embeddings of the frames, and then we are going to have one of the transformer heads dedicated to frame processing. And then the other thing we're going to have is a stack of LSTM cells. The idea being that, and I believe strict hidden state dependency is let me see. Elaborate on this. What I'm wondering is, if we have LSTM cell, then we have MLP, then we have LSTM cell, then we have MLP, and then we get our next action. Are we trying to do, when they say strict hidden state dependency, are we taking hidden states that this LSTM cell is worrying about and then making this next cell dependent on them? That would be my guess. But I was curious about that. The demands persistent serial bookkeeping. Optimization detail being recompute on the fly back propagation through time, as we explored there, keeps activation memory O of 1 in sequence length, enabling thousands of frames despite serial compute. I am not entirely sure what that means. Let's see. LSTMs compute the next state only after the previous state is known. The pair is a hard dependency. And then okay, sure. Okay, so this is just goes back to the hey, like there is a way you can sort of fake this in parallelizable architectures, and it works for some things. And then yeah, the strict hidden state dependency is basically like, okay, we need something in this architecture that can address this problem. So what we're gonna do is take these things which are built to be able to do that, as far as my understanding goes.
I'm afraid I don't quite understand that. Where they recompute on the fly, UPTT, keeps activation memory order 1 in sequence length.
Let's see.
Order 1 in sequence. So the activation memory, basically they're saving. Yeah, okay, so I don't understand that. Recompute on the fly BPTT. I could understand that they're keeping the activation memory for the entire sequence.
Keeps activation memory approximately equal to O of 1 in sequence length. Let's see. What is it? Full BPTT over a long sequence without storing everything in GPU mem. So you stream it left to right in the forward pass and keep it out of VRAM. And then in the backward pass, you recompute the forward activations for only the steps you are currently differentiating through, then immediately free them after taking gradients. Oh, that's interesting. And
yeah,
then,
but each of those forward activations are inherently dependent on all the prior activations. So I don't quite know what it means recompute, unless you save some of them and then just recompute the ones in between.
Just the current steps, working buffers in a tiny state. You recompute the forward activations for only the steps you're currently differentiating through. Recompute the forward activations. My thought would be...
Yeah, no, that's number 3 is saying that. Optionally checkpoint every case down.
Okay,
so
yeah.
so they only rerun K forward passes. Okay.
K chosen as a small constant. Peak activation memory becomes constant, approximately constant, with regards to the sequence length at the cost of extra compute.
Yeah, got
Time
it.
space trade-off. You pay a bit more for compute to cut activation memory growth from O of n to O of 1.
So it's kind of we'll decide a constant number of states that we're going to retain for a backprop, and then we'll recompute the activation states for the ones in between those every kth step.
Yeah, that's what it sounds like to
Yeah.
me.
Yeah. Okay. That makes sense.
Yes. And then, yeah, so we have the sort of like natural split in the architecture here of like we have a frame head, like this thing is parallelizable within a frame. And then we have our temporal backbone, which is sort of our separated stack of LSTMs that really only worry about time. By not caching the frame head activations, we recompute only when we need to in the backward pass, and then we keep the state footprint tiny for a handful of LSTM layers by pure recompute or hybrid offload, store checkpoints, or stream save to pinned host memory as you go forward. Got it. Okay, and then, okay, cool. Sweet. Scaling laws and amortization. Empirically, at fixed parameter count, losses L over S, approximately equal to A of S, and then length negative, what's that, omega S? I don't know. Increasing serial depth, longer train sequences L is a crucial expressivity dimension. At fixed parameter count, increasing serial depth is a crucial. Okay, sure. We agree with that if we agree with vapor up until this point. Longer sequences increase per step wall time linearly, which I did want to ask. Let's see. I don't know what wall time is. Does anybody kind of know what wall time would mean in this context?
That just means runtime. It's kind of like how long is it running?
Okay, got it. Longer sequences increase per step wall time linearly, yet overtake shorter runs on loss versus wall time after a crossover and maintain the advantage. Longer sequences increase per step wall time linearly, but they overtake shorter runs on loss versus wall time after a crossover and maintain the advantage. I think, and when I was discussing, I managed to get a hold of the author this week and pick his brain a little bit about it. And I had to clarify that the in this architecture, longer sequences or like loss goes down, i.e., performance improves as the sequence gets longer, which is sort of unusual based on what we've been working with up until now, i.e., like the more stuff you put in the window, the crappier the thing is at paying attention to the stuff in the window. So it's interesting that this architecture actually enables a like the more you put in, the more you get out kind of thing. Bounded depth time parallel models often degrade as n grows. Yeah. So the idea would be, oh, cool, thanks. I just asked it to make me a presentation file, so a little thing. Let's see. And then yeah, contextualization being agentic systems, internal or like state management is very is critical in these. Otherwise, they get confused. Which if you've used Claude Code in a code base, you will often run into this yourself. In that they're not very good at tracking what exactly is going on and whether or not they need to address something or if they already did. Let's see. There are a couple of ways you can try to address this. This was when I was exploring some related papers. You can add like external state tracking. There's a paper called ACE that relies on playbooks and reflection. And the idea here is with this architecture, we're going to try and solve that internally. And then my instinct that I was sort of direction that I was heading when I was speaking with the author was like, okay, could we, in theory, enhance agentic system performance by having a small, RCFAM module that the agent can like periodically query or like just stream their logs to in such a way where it can sort of detect when it's going to run into one of these problems and then call that one in. Let's see. Retrieval and embedding models, required serial depth, contrast with bounded single vector retrieval. Okay, so this relates to the thing we were talking about last week. Test with fine-grained compositionality, outgrowth static embeddings. Okay, I'm not sure that that's actually relevant here necessarily. Although fine-grained compositionality of embedded frames could be something to wonder about, considering we have some limits with regard to that. And then hierarchical memory. If anybody's heard of an HRM, the hierarchical reasoning model, that's one of the super small models that did really well on ArcAGI. And this targets a continuous perceptual state for next action in dynamic environments. Hierarchical memory focuses on sparse or static knowledge in storage, knowledge retention versus interactive state. So these are not mutually exclusive optimizations to make, as far as I know.
So is that the hierarchical memory? I mean, in the first one, agentic systems, you're talking about kind of this long-term memory capability as being something external, whereas in the hierarchical memory, that's actually part of the model. Is that correct?
The hierarchical reasoning model, let's see, how do they actually do it? Recurrent architecture that attains computational depth and by extracting sequential reasoning tasks in a single forward pass without explicit supervision through recurrent modules.
Is that the same thing? Hierarchical reasoning model, is that the same thing as hierarchical memory?
I believe so, yes. I think this entry came from me having in the notebook this HRM paper, probably, is my guess.
Okay.
But that is also in looking at this, it's kind of interesting here in that a novel recurrent architecture attains significant computational depth while maintaining both training stability and efficiency. So I'm wondering if some of the observations made in here could result in an improvement to architecture of HRMs, which, as I remember, I don't remember or not whether or not these things scale. I know author has not had time to scale this one up, but a curious note, I think. I think that's just about the end of where we're at for me. But the moral of the story is, I don't think it's a revolutionary insight necessarily, but the general idea is like we are for a specific set of very economically relevant tasks and basically anything that you really want to do well long horizon, you need something at the very least in addition to your primary transformer model. And what that something is going to be, the role of that something is to find these sort of like pockets of computational irreducibility and then be able to process them, because no matter how big or good your transformer is, it's not going to be able to do that. The computational cost of sequential fundamentally necessary for demanding long horizon tasks. Yeah. So that's basically the moral of the story. And I guess there's probably some paper sections that might be of interest. But yeah, I guess if anybody's got thoughts or comments or questions, we can just sort of roll through the paper here for referencing jump.
Did you say something about them suggesting some sort of benchmark or testing for this?
Yeah. There's a few benchmarks that they came up with in this paper. Let me see if I can find it. The one that is a so FRJT and then withheld maze position tracking. Let me see if we have it should be in experiments, right? Yeah, forward referencing jumps task. Okay, yeah. Let's see. So for this task, what we will do is generate synthetic programs with a maximum depth of D. It is said to have depth of D if it contains D labels. And then for each math, 8,000 programs will be generated. This is intentional to include short programs to achieve a similar result as teacher, forcing a target program state at each point in time. 1989 citation there. Very nice. If the model has a training signal at all points in time, it is likely to learn the correct transition function. If the model is expected to learn the correct transition function at high depth without intermediates, learning dynamics are more likely to fail. By mixing short and long programs, the circuits learned for the short programs will generalize to longer programs without the need for an auxiliary objective, for example, register state supervision. Then for each block of computation, there exists a jump to a future label. Each block performs 2 jumps, only one of which will execute depending on a condition evaluation. Both jumps will reference forward reference labels. The program halts in either state A or B, depending on the final location of the program counter. To avoid predictability, blocks occasionally jump straight to the terminating state. So that's the kind of benchmarky bit, as far as my understanding goes. However, the program is more likely to jump to a future block compared to jumping to the terminating state, and then more likely to reference blocks closer to maximize runtime, intended that the probability of jumping straight to the end will accumulate. 50% code coverage, halting state. Yeah. Okay, so the binary classification head is going to say, are you jumping? Are you skipping any? If we presume that we have n steps to complete this task, the classifier here at the end is going to be something that's picking, okay, are we jumping? Are we skipping some of these n steps? If so, how many are we skipping? And then, are we going to do that at step n? Are we going to do it at n+1? Are we going to do it at n+2, et cetera, et cetera? And then the thing that we're going to test the model on is, if I give you a sequence with a few different jumps in it, are you able to actually complete the task that the sequence was intended to complete? The idea is we're going to try to force the model to actually calculate sequentially through the series of states that we need in order to get here, because what we're going to do is set those states up such that they are all sort of in series dependent, and then we're going to skip a few every now and again. We're going to see what these models can do. And then, yeah, transformer performance. We have train accuracy, validation accuracy at 65, 59. So I think the highest we're getting is 75. Although at layer 2, embedding dimension is 256 and then max depth of 4, which is interesting to see this progress up until about layer 6 and then start deteriorating right after that. Very interesting. And then we have Mamba here, which is the aforementioned state space model. So we have validation accuracy that seems to be in a lot better shape for a lot longer, and seems to kind of go up and down a little bit, as far as I can see here. Function of layer count for different maximum depths. And then we have LSTM performance, and then the LSTM is yeah, it's got this, no problem at all. Every architecture tested here showed signs of overfitting in every run except for LSTM runs, where only the max depth 32 run showed slight signs of increased validation loss after saturating around 87%. Mamba is able to learn the task up until a critical n, after which layer count has to be increased proportionally. We'll learn the task up to layer n, 1, 2, 3, 4, 5, 6, 7, 8. And then we'll learn it up to layer n, and then you need to start adding more layers to get it all the way through the task. That's interesting. Even the largest model run with 16 layers at depth 16 scores worse than the 1-layer LSTM by a substantial amount, while Mamba at 16 layers cannot be argued to be compute efficient for the task at hand given increasing wall time costs. So we have a lot of like kind of trade-offs that we're making around here. And it's sort of, I think the thing he's sort of getting at is like LSTMs are the like, you do kind of need them here. They're better than all the other ones, basically. We have
Warren,
this second, yeah.
well, I was just going to ask the question, see if I understand what
Yeah.
the experiment is. So they didn't really say what it sounds like there's either an actual machine code that they're running, or they've synthesized some sort of machine code. And then are they feeding the like in order, in memory order instructions to the model, and then asking it to predict something right at the end, which would require state, i.e. branch A or branch B? Is that what they're doing? Like, can you process these instructions and figure out, remember the right state for something?
Let's see. It's said to have depth D if it contains D labels. And then we have
So,
some number of programs.
yeah, it says generate synthetic programs. What type of synthetic program is that?
Yes. So we want whatever kind they are. We want short ones and long ones.
Yeah, I got that.
And then if it has a training signal, yeah, it would be really nice to have. I wonder if maybe do they have like a full data set in here? They might. Oh yeah, and then they have another bench too, actually. I wish that. Yeah, I don't see a data set. I might let's see, let's do a for this task. You explain the FRJT task in more detail. I see shorts, long, and depth measured programs, but I don't have a good picture of what those programs are and what we're testing a transformer on being able to do with that. Let's see. Yes. So second one that they have while our GPT is chewing on that is a maze position tracking task. Same basic principle, 2D grid, predict the position of the agent given a sequence of movements, and then must predict the two components of the final position. Predictions are made after each movement, and then the correct position is teacher forced. Unwithheld maze position tracking task. Model receives not only the sequence, but also whether the movement resulted in an unchanged position. The idea here in this variant, solving the task as simple as counting the number of movements in each direction, excluding the movements that resulted in an unchanged position. All the models get this, easy, 100%, no problem. LSTM, 100% full validation accuracy, and so does a transformer. And then we have our example data here. And then we have the withheld maze position tracking task. The model receives the set of performed movements, but sometimes with a probability P, the resulting movement is withheld. So they get a set of instructions, but they don't get we didn't run into a wall signal, which is basically the thing that we're trying to get to figure out if it can infer here. Maybe in a sequence of movements that cancel each other out, for which it may be possible to build computational shortcuts. And then we have a right withheld. Yeah, so we're doing Here's our instruction, and then here's where whether or not the position actually changed. And then we have our transformers at about 0.6. We have a couple of larger transformers, it looks like, at around 0.9. We again note for clarity that depth does not equal sequence length here, with sequence length being significantly longer than depth, as depth is the count of withheld movements. The sequence consists of both intent and result feedback represented as a token each. Interesting. LSTMs are spiky in accuracy. Heavily discretized objectives with sharp decision boundaries checks out to me. Followed by subsequent fast catch-up, often to a higher accuracy than before. While not included in the comparison, the one-layer LSTM run, despite many spikes, continues to improve, and eventually it's 99%. Let's see. Okay, and then they move on to practical tasks. So, and I think there was, what was the other? There was another bench here, I think, that they outlined. Yeah, diff inflate bench, which I wonder if that got released or not. Just Google that real quick. I am not seeing it. Okay, let's see. Just get back up to our initial question of how does this first one FRJT thing work? Okay. Think of each example as a tiny straight line program made of blocks labeled L1 to LD. Compute a condition, 2 forward only jumps, no backward jumps, no loops. Exactly one of those 2 jumps is taken depending on the condition, and then may jump directly to halt A or halt B. The program counter begins at L1. Because jumps are forward referencing, you cannot know which label comes next until you evaluate the current block. Because we have the probability of jumping directly to halt, and since that could happen, we have to evaluate each block. That's the idea. All jumps go forward and never back. Run halts in A or B, and then bias the jumps to be forward and relatively local. And then shoot for 50-50. Does that clear up the question there, Raj?
Warren, if you go to the figure 1 of the paper, I think that might be an example of the what do you call that? This thing.
Let's see, figure 1 in the paper. Let's see. That's 2, right? So where's my 1 here?
The one I'm looking at the PDF version. The one is on page 8.
Figure. Let me see if I can do. There we go. There we go. We got it. This guy. Okay, input length proportionality. Does it look like this? The true sequential op, label 1, label 2, that kind of thing?
Yeah, that's the one I'm talking about.
And that is for input length proportionality. Implies sequentially applying a transition function some number of times that is proportional to the input length n, and parallel aggregation is not possible. So this is supposed to be a sequence of n instructions modifying the state of the variable, and then interspersed with queries about the current states. Result of the queries may affect the state of the variable in subsequent instructions or be independent of it. A language with the following properties may look as follows. Result of these queries may affect the state of the variable.
So kind of an assembler like register manipulation and jumping.
Yeah, I think
type of made up language. Yep.
Yeah, I think the way that one of the models had described it to me was a pointer chasing task, which sounded fairly accurate to me.
Okay, thanks.
Control flow depends on basic idea. Control flow depends on the result of the previous instructions. They might execute or they might get skipped. And then we only allow forward referencing jumps. So we're in a DAG here in the normal way.
Makes sense.
Indeed. Let's see. Okay. Relevance. I think we were down-ish here, right? Yeah, experiments. Maze position tracking. Yes, that is a good one. Withheld maze position tracking. So basically the commonality between all of these is like we have a sequence. We are doing some computations over the course of the sequence, and then what we're going to try and do is get the transformer to figure out what the right answer is when we hide some portion of the sequence. Like, can you learn what's supposed to go there kind of thing.
So essentially the state has to capture what does the maze look like in addition to tracking the state.
Let's see. It has left unchanged. So the state that it would track, so it's going to need to track the position of the agent. And as such, it's going to need to infer what the maze actually looks like to figure out whether that instruction to the agent actually would result in a position change or not.
Right. Yep.
Let's see. So a couple of practical tasks being coding agent task, and I think the other one is diff inflate bench. Yeah. So coding agent task is very relevant to my interest personally. They observe the state of the computer through a series of text-based console commands and their respective outputs. Every command and every file system modification, we're going to make an assumption here, compared to the system's initial clean state, is performed exclusively by the agent. Every line of code could be assumed to have been written by the agent itself. Depending on the exact representation of the agent's observation, modifications may either occur in the form of diff strings or in the form of partially rendered text file contents through position seeking functionality, i.e. the text editor. So we're working with git diffs or we're working with file patches. Only view of a file is the sequence of diffs, each of which patches the current file state. Formally, the file state S is computed as empty file, S of t. We're going to apply each step in sequence, and then t is our time is 1 to n. Patch representations are known to be applicable in parallel in many cases. However, a clean sequence of diffs is rarely observed in practice. In practice, executing commands induces side effects to the state of the file system, which we will assume will not be directly observed by the agent. Doing so would require intercepting file IO system calls, which is not feasible in practice, but this induces strict data dependence into the problem because now we do need to track and materialize a sequentially consistent history of the file system to answer questions about the command's behavior at time t, even if only semantically as opposed to literal neural emulation. Formally, we now have two stages, one being patch application given by partial observations, and the second being optionally present side effect, which accepts the state of the file system at time t and returns a new state of the file system at time t plus 1. The moral of the story here being, yes, when you might be able to apply all of the patches out of order, but if you do, there are side effects of the current state of the file, and you're going to mess up some of those side effects or not take them into account properly if you're just kind of guessing at what orders these diffs are supposed to be in, rather than actually tracking state and then learning what is actually supposed to come next. Given that we are frequently rendering, let's see. This problem in particular can be sidestepped through a full print of the file's contents initiated by the agent, which, yes. So basically what I'm kind of looking for is like, can we find a way sort of around this limitation and then build that into a harness? That's kind of where my head's at with this. But the inability to aggregate its history, we're confronted with the fact that the agent cannot possess a true representation of the codebase's trajectory. We are left with a strictly atemporal representation of the codebase, void of true cross-temporal context as time approaches infinity. Inability to aggregate its history. So yeah, I was like, okay, well, let's give it the ability to aggregate its history. We have a new benchmark from them that is we're gonna ask a model to produce the final state of a file given a sequence of Git diffs. The final state is given to a judge, which is tasked with determining whether the candidate prediction is functionally equivalent to the ground truth final state. Formatting and style differences are allowed. Semantically relevant changes are penalized. Candidate predictions were manually inspected for surface level intactness compared to ground truth final state to rule out context length induced truncation. Let's see, equivalent to copy operation, estimate the fraction of correct renderings, deliberately use patches from tinygrad. So yes, tinygrad was their selection for what's not going to be in the training data already, for throwing a transformer at patching modifications too, which is kind of interesting. We have a concerning trend that for other repositories, performance does not degrade as rapidly as it does for tinygrad. We believe this is due to the fact that for code bases of lower complexity, the model is able to guess the correct final state and aggregate primarily by plausibility as opposed to true state tracking, which I think is kind of the core question limitation thing here. It's like, yes, if we're going to acknowledge that there is some kind of limitation in what can be represented in the latents of this network, but operationally, can we get around that by sort of guessing or inferring what was supposed to happen if I was actually capable of doing things in sequence, as opposed to actually doing that sequential computation, which is normally, or like sort of in my experience with transformer models, usually what they end up being able to do a surprisingly good job at for things that they're not supposed to be able to do. Let's see. Sufficient chain of thought. Model could externalize all state tracking. So there's the other thought is like, okay, well, if we try to make the neural network actually learn how to do sequential stuff, it's not going to be able to, but you can just have it think in order and then sort of cross your fingers that that's going to work out. Facilitate the correct inflation of disk. However, this is not the point of the benchmark. GPT-5 codecs and mini. So we have a few of those with codecs as the judge. And then strict downward trend in performance as the number of diffs increases, as one might expect. As the number of patches increases, the code base becomes increasingly opaque to the model. 4.5 is able to better maintain accuracy throughout. Interesting. And then task is not impossible to solve in parallelizable fashion. And then the act of generating the final state of the code may help to sufficiently decompose the problem over many tokens, given partial results in ways which are not necessarily comparable to the more immediate perception requirements needed during an agentic workload. So we note that this benchmark is likely an insufficient measurement of true codebase embedding quality. Appears to start with the current file region. The surrounding context allows the model to cheat as it effectively leaks the state of the surrounding regions at a given point in time, eliminating the need for true state tracking for the regions covered. Yeah, so that's really my primary question here is like, okay, yes, I'll give you that there is no internal mechanism for a transformer model to learn like a sequential computation through a series of states in the way that we are describing this failure case. But if it cheats good enough to where I don't have to worry about it, I'm kind of fine with that. That is basically where I'm sitting at.
Am I understanding that correctly though? It only becomes the problem for a transformer if the sequence exceeds the sequence limit of the model, right? it should be able to maintain that state. My intuition, at least, is that it should be able to maintain that state as long as the entire sequence will fit into the KV cache. It should be able to address anything in that sequence.
I
So that
believe, yeah, I believe that the I believe that that is correct, but I think that there it may not be exactly that sequence length of sequence length n, where n is less than the amount of the total length I could fit in my KV cache. Because we have this little input aggregation criticality occurs after a number of need to be performed. Let's see. After the number of true sequential operations that need to be performed to correctly aggregate the input data exceeds the constant number of true sequential operations the model can perform as a function of its layer count. So, I don't think it's necessarily dependent on KV cache load sequence length, and
Oh, I
more
see.
dependent on, is there enough layers and then enough throughput between the layers where you can stay coherent if you're actually trying to compute this series of state changes. It's kind of where what I'm thinking.
I see. So for operations that require sequential, you need to have enough layers wherever they are in the sequence, but you still need to have enough layers to kind of do the aggregation of those steps.
Yeah, how I'm thinking about it is like from layer, let's say between layers 4 and 5, I'm gonna need to represent state A, and then I'm going to need to represent let's call it state B, but it's just a small change to state A. As long as that tracking of that sequence happens between, let's say, layer 4 and layer 20. Then I can keep all of that coherent enough for that duration to be able to get through it, basically. But once I get to if I'm trying to go from layer 4 to layer 21, that's when I start breaking down, because I can only hold that 4 to 20 sort of length in my reasoning bits, I guess, is that's at least how I've sort of got it in my head, at least.
Okay. I think I see
I
that.
don't know whether
So
I don't know how accurate my head picture is, though, but that's what I've got.
yeah.
Let's see. An argument from video, which I think is possibly kind of interesting here. Input sequence is stored in full. May be very feasible to hold a sequence of text tokens in memory at once. Not the case for video. Video is heavily compressed. Keyframes necessary for frame interpolation inflate to full size. To serve as a training example, to avoid memory explosion, model architectures will have to be streamable in the same way as video decoding is. Longer training horizons should neither require more devices nor significantly more memory beyond what is required to store the compressed video data. This is practically achievable with left to right streaming recurrence. Sorry. Yeah, I'm free in like 45.
Huh?
Yeah, I'll be free in like 45 minutes or something.
45 minutes?
Yeah.
Yeah.
Okay, sorry about that. Let's see. We've got let's see. I want to reread this here. So, computer efficient time parallelism in practice implies random access to the input sequence. In many training procedures, input sequence is stored in full. Feasible for text, not the case for video data. Video data is heavily compressed, and then we inflate keyframes. Model architecture. Okay, so the argument here is maybe for video understanding, you want your model architecture. You want your model architecture. Therefore, the decompressed to serve as a training example. Your model architecture will have to be streamable in the same way as video decoding is. Store compressed video. It's practically achievable with left to right streaming returns. What exactly? Implication skills. That's interesting. I'm not quite sure how to interpret, but it sounds interesting. So we'll see what GPT has to say about it. Let's see. And then we have diff inflate down here, I believe. Yeah. Coding agent task, diff inflate bench. Can cheat. To test whether this is the approximation that it's learned, configure Git to produce minimal diffs without redundant context. Moving the task away from reflected in observation and towards withheld but inferable. The result is a collapse in accuracy across all models, including 4.5 sonnets. We note, however, that relying on solely line count arithmetic for inferring patch placement is potentially harsh. Yes. We therefore also evaluate diffs with exactly one line of context, allowing placement to be inferred from context while still reducing the likelihood of leaking too many lines. Let's see. We do not argue that U0 or U1 should be used in practice. The specific failure mode exhibited here should be understood to apply wherever actions result in effects that are not sufficiently reflected in the observations and require mental bookkeeping. Test whether, what I'm curious is when they say this is the approximation, what's the approximation exactly that they're talking about here? Insufficient, given a sorted set of diffs. Repeating non-deleted lines from the latest diff that appears to start with the current file region to be rendered would represent a parallelizable approximation that is learnable by a transformer. That given a sorted set of diffs, repeating the non-deleted lines from the latest diff that appears to start with the current file region would be parallelizable. Repeating non-deleted lines, non-deleted. So show me lines that did not get deleted as a result of the latest diff. If it starts in the current file region, then that tells me where the diff stops, I would think. Effectively leaves the state of surrounding regions at a given point in time. Parallelizable approximation. Okay, so what it is going to learn about diffs is that when I apply a diff for the lines that don't get deleted, that seem to start with the current file region I'm looking at, will let me figure out in what order I should apply these diffs. I'm gonna chew on that a little bit more, I think, in the future. Is there like a thing that's occurring to anybody about this thing? This feels interesting to me, but I'm not sure why exactly. Okay, thank you. We'll have to look that up a little bit later. Many times steps at once. Just either pre-inflate a large chunk or the whole clip into large frames so you can redecode. Okay.
Warren, it occurs to me that the exact details of the experiment, I'm not sure I'm tracking, but in general, they've set up a number of very toy experiments.
Yeah.
That they're trying to use to test the point, but I don't know. I'd be interested to see the other sections, like the nuance, chain of thought, and the conclusion. But the place where it seems like you really want to know is, how does this impact like the language model, those, the things at those scale rather than the toy.
Yeah, I think when I was talking with the author, he mentioned that as well. He was like, yeah, I kind of had to rush it out the door. There's a lot more that I would have liked to explore. I was just kind of like compute constrained, and then I need to write like some new infrastructure cut, largely because most of the like large scale training our infrastructure that currently exists is not built with recurrence-complete model training in mind, I believe is what he was saying. But speaking of, let's see, we have a couple of training implementations here, or implications from our video analogy here, which is, okay, like we like recurrence. Yep, sure, cool, thanks. True depth, global attention across all time steps once. If you push for time parallelism, you end up engineering around the codec and you still won't get the true depth needed. And then you want to make your sequence length scale with memory at O of 1 if you can. Streaming plus recompute on the fly BPTT. So activation memory doesn't grow with clip length. Keep a small Windows activations, recompute the others. And then you will be able to do training with and take advantage of that parallelization. And then some interesting insights with regards to training stacks. Let's see, nuance of chain of thought. Let's see what we got here. Chain of thought-like mechanisms can serve as a form of memory, which it can learn to utilize to externalize state tracking operations. Yeah, that was basically where I was at with it. Verifiable rewards have been used to optimize for better chains of thought, improving performance of downstream tasks. For tasks where the tracked state is trivially represented in text, transformers with chain of thought can solve it in theory and practice. Input aggregation criticality remains a fundamental perceptual limitation whenever the next token is generated from the current context. Any prolonged chain of thought is therefore under constant pressure such that the number of sequential operations required to decode said context remains constant to avoid loss of information. Is under constant pressure such that the number of sequential operations required to decode remains constant. Okay, okay, so the chain of thought is sort of being instructed in such a way where if I can only track this sort of like sequence based on like what my layers let me, then I'm gonna end up building my whole chain of thought with that limitation in mind, is kind of what I'm reading out of that. It is misleading.
So it kind of seems like what they're saying is that this constraint about like the number of layers and the input aggregation being related to the number, or what do they call it? Aggregation criticality being related to the number of layers. Chain of thought, when it's actually in the inference phase, it can actually insert aggregated state into the stream, in this case through chain of thought, which is then referenceable.
Oh, interesting. Okay, so we have that. We have the initial like layer-based limitation of that is the input aggregation limit.
Right.
Normally, when we're producing next token, normally we can go, let's say, from layer 4 to layer 20 or whatever. But as part of chain of thought, what we can do is what we currently have right now is 4 to 20. If I can encode that into this chain of thought so that I can reference it later, then I can encode 4 to 20 and then actually hold like 20 to 25, and then be able to reference that in parallel later of that 4 to 20 that I encoded. Is that kind of what you
That's
were
what I
getting?
would. That's where I was going with this. Yeah,
Yeah.
yeah. So the chain of thought is kind of a way of summarizing what you have. You've already inferred already based on some input tokens. You've aggregated them to some level, and now you can reference those at the next token generation. So
Hmm.
it kind of allows you to, and I never thought about it this way, but in a way, it kind of allows you to make it a deeper model because the state is generated and inserted into the input sequence again.
Generated into the input
And
sequence.
I mean, it's true. It seems like we know that long sequences, the quality degrades. It becomes more and more difficult to pull the specific details out of a long sequence.
Hmm.
But on the other hand, recurrent models also have the same problem based on the size of their state. They can only only cram so much state into a state vector of a certain size.
Yeah. And then yeah, and the thought there being like so you can sort of overcome by sort of freezing some of that state into this sort of chain of thought that you've got to work with. Um, but but yeah, there's still some number of computationally irreducible sort of operations that you will still miss because even if you can freeze and you have a certain length that you're able to compute, then whatever's in between the length that exceeds your ability to compute and something that you can sufficiently encode frozen bits of and then be able to do that computation to the point where you're able to solve the where you're able to actually get to the answer.
So
Um,
you're thinking like if the chain of thought exceeds the length of the maximum sequence for the model, then you can't solve the problem.
how I'm what I'm thinking is, let's say I can do in my neural network, I can do layer 4 through layer 20, and that is my max sequence. What I'm thinking is four things that if I take my thing that I have between layers 4 and 20, and then I can encode some components of that while I'm doing chain of thought, then I can give myself I can freeze portions that I can then add hey, I'm capable of 4 through 20 reasoning here. So if I can freeze like 1, 2, and 3 as I'm thinking, then I should be able to pay attention all the way through effectively up, 1 through 20 kind of deal. But for things that um, are not, for things that I would have missed because I don't have that capability of going past from 4 to 20, since if for things that I would need a from 4 to 21, I'm going to miss all those. But for things that if I were to compute the first part and then I can finish it out with my 4 through 20, then I can get those. But the population of things that needs a 4 through 21 will still be inaccessible, is kind of where
But I guess I'm wondering if you can take, step 20, and you're able to they're calling it chain of thought, but let me just think of it as, um, I guess chain of thought is maybe the right description, but basically you're taking 4 through 20, you're producing some result that you insert into the sequence, and now you're able to take that and combine it with the 21 so that you get you can handle 21 steps.
Mhm.
It might be interesting to be thinking of chain of thought as a way of um, increasing the depth of this, whatever they call it, the aggregation
Mhm.
criticality.
Well, yeah,
Did you?
and I guess like to extrapolate a little would be there might be there's some operations that if we took the same transformer as the one we're working with right now, and if we could just add like, a few extra layers of depth, then we would be able to solve this problem. Um, Maybe worth filing away that, hey, like you can sort of kind of simulate some of that capability by sort of training that into your chain of thought that your model is going to produce. What do you
Right,
think?
and maybe you train it differently because right now chain of thought kind of seems like it's mimicking a human chain of thought, and somehow that makes
Yeah,
the answer better. But if you thought of it instead as increasing the depth of this aggregation criticality,
yeah. Hmm.
maybe you could train it to generate text that loads in the sequence that isn't necessarily what we would do with chain of thought, but is allowing them to kind of, aggregate the state, insert that back into the sequence, and allow me to do more aggregation on top of it.
Yeah, actually, that makes a lot of sense actually to me. Where it's
Yeah,
like the way, like currently the way that we do chain of thought is like, oh, well, when I'm a human and I think for more, I get smarter.
right.
It's like that has nothing to do with this computation that you're performing here. But what is related to that computation is this quality of input aggregation criticality, where if so in theory, so a thing that I guess one could propose is that the thing that the models are actually doing with that, like, hey, humans think, you should think too, sort of section is the thing that they've learned to do with it is to shore up some of the holes in their ability to do that kind of sequential processing
Right.
of insufficiently parallelizable tasks, kind of thing.
Yeah. Yeah. Interesting.
Indeed. Let's see. Well, yeah, I guess
So
we're kind of
yeah,
rounding up on the hour. Anything,
yeah.
any spots? Yeah, any
Can you?
thoughts?
Yeah. We're up 8 o'clock. So, do you want to? Is there conclusions? Can we zoom through the
Yeah,
conclusions real
yeah. Let's
fast?
hop over to that and see what we got. So conclusion. Long horizon perception and control demand true serial computation. That is a strong claim. I'm not sure it does. But the there are some serial computation limits when it comes to transformer models. I'd agree with that one. We formalize this with true depth, inherently sequential steps, and then recurrence completeness. Can we realize general non-associative recurrent updates? From these definitions, we prove three impossibilities. Parallelizable forward or backward cannot be recurrence completes. Parallelizable or scan-like input aggregation are also excluded. And then constant depth transformers, SSMs, parallelizable RNNs are insufficient in the worst case, is an important clarification, I think, there. We further introduce input length proportionality and input aggregation criticality, predicting a critical horizon beyond which non-recurrence complete models fail to form correct state. And that's the thing that we're getting at, and we're saying for some things, you need to be able to form that correct state, and there are some states that you will never be able to form, are the things that I would agree with here. Diagnostics that force serial evaluation exhibit depth-dependent cliffs, and then a lightweight LSTM generalizes substantially further. Attention within frames, LSTM over time, trained on GitHub derived text video shows a clear power law in train sequence length at fixed parameters. Longer sequences uniformly improve early and late positions and ultimately amortize their linear wall time cost. Taken together, the theory and its results indicate that serial computation is not only necessary, but potentially beneficial to increase model expressivity, which I would agree with, I think.
So the two things that I'd kind of like to see there is their critical aggregation criticality. It'd be interesting to see if I understand the way you're describing it. It's a function of the number of layers,
Mm-hmm.
assuming the sequence length is sufficient, but it's the number of layers. It'd be interesting to demonstrate that with um, identical models with a different number of layers and show that the aggregation criticality changes.
Yeah, no, that would be interesting. I.e., give this one 15 layers, give this one 20 layers, and then for the aggregation criticality, let's see if we can measure what that critical mass is, and then measure whether or not that's different across the two models. I think would be
Right. And then
yeah.
secondly, come up with some sort of um, uh, not chain of thought, but thinking out loud or something, something that says, could we come up with a way to train it to use injection into the sequence to extend that criticality depth?
Yeah, yeah. No, I think that's
That,
actually super interesting.
that'd be a fun experiment.
Yeah, I might send that over to the author and see if he's keen to iterate on there a little bit. It'd be kind of fun.
So could you use this in your current project?
Well, for me, not this specific. Yeah, so like the thing that this points out for me is, hey, for some kinds of some kinds of things that you might need to learn in an operational setting, you have some limitations on your architecture is simply not going to be capable of learning like worst case scenario type stuff. But yeah, mostly the way for me is yeah, I think approaches like Rogers are interesting, and like one of the things that I do when I'm working on when I'm either using or building coding agent harnesses is I will almost always have some kind of external state tracking, oftentimes like get integration with like GitHub or Linear or whatever. But I think it is interesting to note that I think it'll be for like if I know I'm writing code and I'm about to have Claude try to write something that's going to have a lot of side effects and that you need to be able to sort of think through A, then B, then C, then D, I'm probably going to like watch him a lot closer and then force him to use his notepad more often kind of thing is currently how I'm having this inform my day to day. But more of like a curiosity, I think, just because I think that this explains some tendencies, but doesn't necessarily like reveal a critical vulnerability necessarily. And then even if it does, like presumably I could just train one of these kinds of models as an external module and then have that do some monitoring of my primary agent.
Makes sense. What was the agent you were talking about for doing Notepad? Was it Notepad or note taking or something?
But well, I didn't have a specific agent in mind. I have for all of the agents that I use, I always give them like a scratch pad / journal, and then for some I have like a fairly sophisticated kind of cold hot memory storage sort of setup for them.
Okay. Is that just like in a file, or do you have a service you use for that, or what?
Yeah, it depends. So late or my most recent kind of exploration has been Claude Code came out with skills this week. So I am experimenting with having my Claude do skill generations, and then like some of those skills that I have had it generate are related to like how it does long-term storage. So I have like a couple of like MCPs and then one CLI that I have it to get into the weeds a little bit, I guess. The way that I use them now is I use a standard called OpenSpec, and then I have a CLI called Beads, and then I have a MCP called Serena, and then I also use Linear and GitHub like issues, etc. And then I also have the Scratchpad folder. And then between all of those things, those perform different roles in terms of like long-term storage and memory and other kinds of like optimization of things other than produce the next token robot kind of thing, basically.
Gotcha.
Well, yeah, I guess I Unless we had any final thoughts, I'll cut my recording and we can figure out if who we've got for next week, if anybody. Or do we already have someone? I think we do.